Long since Galileo Galilei first turned a telescope toward the night sky over 400 years ago, astronomers and people alike have wondered what secrets the other planets in the solar system could hold. For nearly all of human history, we have only seen the planets as points of light in the night sky, so-called wandering stars because of their peculiar movements relative to the distant background stars over each calendar year. It wasn't until technology came far enough that concrete ideas could finally begin to take shape for what space outside the moon's orbit would look like. While discoveries of the solar system came slow at first, with Uranus, Neptune, and Pluto each not being found until 1781, 1846, and 1930, the advent of rocket technology soon unlocked a new way to study our local neighborhood. The first concepts of interplanetary travel came from scientists like Germany's Wernher von Braun and Russia's Konstantin Tsiolkovsky, the latter of whom inspired von Braun with ideas of using rockets not for war but for science. Tsiolkovsky was likely the first to envision an interplanetary exploration with rockets, realizing their enormous potential in the late 19th and early 20th centuries. His groundbreaking 1903 publication, Exploration of Outer Space by Means of Rocket Devices, was the first to suggest that rockets could be used for spaceflight, developing some of the initial concepts of multi-stage liquid fuel rockets. By setting the stage for humanity's earliest aspirations to explore the planets, Tsiolkovsky has been heralded as the founding father of modern rocketry, influencing nearly every person involved in spaceflight since his publications. Early serious proposals for interplanetary exploration emerged in the late 1950s and early 1960s, spurred on by the success of the Soviet Union's Sputnik and the United States' Explorer missions. These first spacecraft proved that we could not only put objects into orbit, but we could also perform scientific measurements in space and relay data back to the ground. However, due to launch capability constraints, it would be some time before the first spacecraft successfully left the Earth-Moon system. Both NASA and the Soviet Union viewed planetary exploration as a necessary goal for scientific study. Still, funding and focus were lacking, given the all-important goal of being the first to put a man on the moon. Various efforts by both NASA and the Soviets to increase launch capabilities and improve guidance control culminated in the first interplanetary probes, the Soviets' Venera 1 and NASA's Mariner 2, both passing close by Venus in May 1961 and December 1962 respectively. These missions proved that precise interplanetary travel was now feasible and thus began a separate space race for uncrewed spacecraft to other planets. Early in NASA's history, scientists still had yet to prove that travel to the moon by any spacecraft, whether carrying humans or not, was even possible with the technology available. Out of this came the Pioneer program, NASA's first attempt at achieving Earth's escape velocity, leaving orbit, and studying the moon up close. The program came in two phases, an initial attempt to orbit the moon and a latter phase focusing on exploring the outer solar system. Early Pioneer missions were stepping stones toward what would become more ambitious interplanetary goals. First launching in 1958, Pioneers 0, 1, and 2 were the first attempts by the United States to reach the moon. These, unfortunately, all ended in failure. Pioneer 0's mission ended just 74 seconds after liftoff due to the booster exploding, resulting in the complete destruction of the probe. And Pioneers 1 and 2 survived the launch into space, though failures of both third stages resulted in Pioneer 1 missing the moon entirely, and Pioneer 2 re-entering Earth's atmosphere just 42 minutes after launch. Pioneers 3 and 4 each shared a similar design, which differed from the first three. Spin stabilized, the probes were intended to succeed where the initial Pioneers failed, most notably in the launch portion. Lifting off in December 1958, Pioneer 3's boost phase out of Earth's atmosphere went according to plan until the first stage shut down early, which left the spacecraft without enough velocity to reach lunar orbit. Reaching just 102,000 kilometers over Earth, or a little over a quarter of the distance to the moon, Pioneer 3's mission wasn't declared a complete failure, as it still sent back crucial data about the Van Allen belts, which are donut-like rings of radiation around Earth. Pioneer 4 followed in March of 1959. Similar in design to its sibling probe, Pioneer 4 was the first of the program to successfully meet the overall goal of reaching the moon, making it the United States' first spacecraft to leave Earth's gravitational sphere of influence and the only success of 12 attempts between 1958 and 1963. As it passed within 60,000 kilometers of the lunar surface just 41 hours after launch, Pioneer 4 transmitted radiation data, giving scientists an idea of the conditions future lunar astronauts would have to endure over the length of their missions. The spacecraft continued to send data for nearly 2 additional days before power was lost about 660,000 kilometers above the Earth's surface. However, had the battery life been increased, it's thought that the probe could have sent reliable data from nearly double that distance. Pioneer 5 was the last of the first phase Pioneer missions not to see critical failure during launch. Other missions were conducted before the end of 1960, Pioneers P1, P3, P30, and P31. However, they all either partially or totally failed.
2, 1, 0.
Pioneer 5, launching March 11, 1960, is heralded as the most successful of the first phase missions. Unlike before, its original proposal was to study Venus in November 1959. Unfortunately, the launch date was pushed back 5 months due to technical issues, and the window to Venus closed. Despite this, NASA continued with Pioneer 5's mission, aiming to investigate the interplanetary space between the Earth and Venus. The launch of the probe went smoothly, and it was put into an orbit between the 2 planets. With an onboard magnetometer and cosmic ray detector, radiation data was collected in interplanetary space for the first time. Pioneer 5 provided the earliest confirmation of interplanetary magnetic fields, as well as measuring solar flare particles and cosmic radiation in the region. The spacecraft was heard from for a final time on June 26, 1960, over 3 months after launch, from a then record distance of 36.2 million kilometers. Pioneer's first phase ended with the unsuccessful launch of Pioneer P31 in December 1960. Then shelved for 5 years, the Pioneer name finally revived when NASA's Ames Research Center began a series of missions under the same title. Seen as an extension of the initial Pioneer probes, this follow-up phase held greater ambition and loftier goals than missions 0 through 5. The first goal of the new Pioneer program was to study interplanetary space weather in greater detail, such as the conditions of solar wind and cosmic rays. Missions 6 through 9, also noted as A through D, were launched between 1965 and 1969 into solar orbits, where they provided long-term observations. It was revolutionary data that helped scientists understand concepts and topics concerning solar flares, particle radiation, and how solar wind impacts Earth's magnetic field. Pioneer 6 was the first of several U.S. spacecraft designed to study regions of space around the Sun. Launched on December 16, 1965, it was followed by 7, 8, and 9 in August of 66, December of 67, and November of 68. Missions 6 and 7 were very identical and focused on measuring solar wind particles and carrying out long-distance communications experiments. However, they both achieved separate yet groundbreaking feats. Pioneer 6, for instance, stands as one of the longest-lived missions in history after it was last heard from in 2000, and 7 came within 12 million kilometers of Halley's Comet in 1986, the closest U.S. spacecraft to do so. Along with Pioneers 8 and 9, the 4 missions formed a solar weather monitoring program along Earth's orbit, measuring and predicting solar storms for various customers like the FAA, power companies, and more. A 5th mission, dubbed Pioneer E, was planned to be part of the series, but it was unfortunately lost during launch and thus not given a mission number. These 4 extraordinarily successful missions cemented NASA's knack for interplanetary exploration and worked as the foundation for many future missions in and outside of the Pioneer program. NASA's aspirations began to shift in the late 1960s toward a more profound goal, sending probes not just to the moon or into orbit around the sun, but to the distant gas giants of the outer solar system. This ambition culminated in the development of two key spacecraft, Pioneers 10 and 11, initially designated as Pioneers F and G, which would push the boundaries of space exploration and lead the way for a slew of future interplanetary explorers. As envisioned by JPL engineer Gary Flandreau, a potential mission dubbed the Planetary Grand Tour could exploit a rare alignment of the four gas giants, flying by each and gaining a boost toward the next, working its way by all four of the outer planets in one launch. Though eventually accomplished by NASA's Voyager missions, which were heavily inspired by the Pioneer designs, the Grand Tour idea accelerated the space program into developing interplanetary capable spacecraft. Several technological breakthroughs in the years before Pioneers 10 and 11 allowed the Grand Tour to come to fruition. Newly developed radioisotope thermoelectric generators, or RTGs, allowed missions to operate far from the sun, where light is too dim to power even the largest solar panels on spacecraft at the time. Additionally, advanced computing technology, the further miniaturization of computers, and the development of precise trajectory control all culminated in the ability to navigate the outer planets, predict flyby trajectories years ahead of time, and provide spacecraft with greater computing power. Lastly, upgraded spacecraft design and new material technologies allowed spacecraft development capable of withstanding intense radiation and the harsh environments of deep space. This would be especially important for Pioneer and later missions during their encounters with Jupiter and Saturn, each of whom boasts massive radiation belts capable of entirely frying unprotected electronics. To prepare for the Grand Tour idea, NASA planned to use Pioneers 10 and 11 as test missions for the upcoming Voyager program, which would take the Grand Tour route, flying by all four outer planets. To meet the scheduled Jupiter arrival date of December 1973, NASA awarded their Ames Research Center with management of the program in February 1970. Ames then granted $380 million to the contractor TRW Inc. to build the two spacecraft. Planning and construction took an estimated 25 million man-hours to accomplish, and as an engineer from TRW said, this spacecraft is guaranteed for 2 years of interplanetary flight. If any component fails within that warranty period, just return the spacecraft to our shop and we will repair it free of charge. The design for 10 and 11 was relatively simple. Pioneer was built around a 76 centimeter by 36 centimeter hexagonal bus, which housed propellant and most of the scientific instruments, and was wrapped in protective thermal insulation made of mylar and Kapton blankets. The spacecraft itself was heated by the energy dissipated from the interior electronics, and to power Pioneer, 4 RTGs positioned on two 3-meter-long trusses were used to provide 155 watts, which decayed to 140 watts by Jupiter flyby, far exceeding the performance requirements of 100 watts for all systems to nominally operate. Lastly, a large 2.7-meter dish on the spacecraft provided the main communication line back to Earth, though at a measly transmission rate of 256 bits per second, which only decreased as the spacecraft raced away. Launching on March 3, 1972, Pioneer 10 took a direct route into the outer solar system. It passed by the moon in just 11 hours, moving at a blistering 51,682 kilometers per hour, or 32,114 miles per hour, and thus becoming the fastest human-made object up to that point. It quickly began powering up its instruments, and throughout its journey to Jupiter, Pioneer 10 made a wide variety of observations. Experiments measured cosmic rays, magnetic fields, solar wind, and the zodiacal light, and calibration of the imaging instruments were conducted. Pioneer 10 became a mission of firsts: the first spacecraft to pass Mars and enter the asteroid belt, the first to detect helium atoms in the interplanetary medium, the first to measure solar wind beyond Mars, and, beginning in November 1973, the first to reach Jupiter. Instrument testing began on November 6th, with the first images successfully received by the Deep Space Network. With each passing day, Pioneer 10 flew closer to the planet, reaching Jupiter's immense magnetic field on November 16th and passing the outermost moon's orbits by the 29th. On December 2nd, images taken by Pioneer 10 began exceeding the best quality photos from Earth, providing never-before-seen details of Jupiter's clouds, and more than 500 images would be taken during the encounter. As it passed by Jupiter, Pioneer 10 also experienced intense radiation from the planet. The peak flux of the electron radiation, which, as it's named, come from electrons, was 10,000 times stronger than around Earth, and throughout the flyby received 200,000 rads from electrons and 56,000 rads from protons. For reference, humans experience a fatal dose of radiation from just 500 rads. These measurements were 10 times greater than engineers anticipated, and its effects could be seen as false commands began to generate. Luckily, most were corrected by quick commands from Earth. However, several images were ultimately lost due to corruption. The spacecraft survived the encounter, though, and made numerous observations of Jupiter's cloudy atmosphere and several of its moons. Close images of Ganymede and Europa revealed surface features never seen from Earth. At its closest approach to Jupiter, the spacecraft reached a velocity of 132,000 kilometers an hour. Though this was the end of encounters for Pioneer 10, scientific recordings continued for decades past the planned 2-year mission profile. Crossing Saturn and Uranus's orbits, it reached Neptune's orbit on June 13, 1983, becoming the first spacecraft to pass outside the bounds of the major planets. Over this time, many instruments no longer needed were shut off to conserve power. However, a few continued running into the end of its life, and contact with 10 continued into 2003. Though the last successful reception of its telemetry data was received in April 2002, when the spacecraft was more than 80 times the distance from the Sun as the Earth, its last contact was made on January 23, 2003, when a few faint signals were sent back home, just barely strong enough to detect. Pioneer 11's design was essentially identical to 10's, acting as a twin probe. Its primary mission would involve passing by Jupiter as 10 had before it. However, it would take a different path onward, eventually becoming the first spacecraft to reach and fly by Saturn. Launching April 6, 1973, just 1 year and 1 month after 10, 11 took a direct route to Jupiter as its twin had. Over November and December 1974, 11 flew by Jupiter, passing just 42,828 kilometers or 26,612 miles from the clouds. Taking a north-south route around the planet, it returned the first images of Jupiter's polar regions and obtained detailed observations of the Great Red Spot. As 11 flew over the raging storms, it utilized Jupiter's immense gravity to slingshot itself towards Saturn. By the time Pioneer 11 reached Saturn in August and September 1979, Voyagers 1 and 2 had already launched and passed by Jupiter themselves. Because of this, it was decided that 11 would pass through the planet's rings. This would test the route before the Voyagers, who would take the same path, arrived. Thus, Pioneer lived up to its name's truest sense, becoming a pioneer for future endeavors. As 11 passed closer to Saturn over August of 1979, it began capturing detailed images of the planet, far surpassing the resolution obtainable from Earth-based telescopes. And, as 10 had done at Jupiter, Pioneer 11 made numerous discoveries about Saturn and its many moons. One moon, Epimetheus, was discovered in images the day following its closest approach. The spacecraft also nearly collided with Epimetheus, coming just 4,000 kilometers or 2,500 miles from the moon. It later flew by moons Janus and Mimas, and discovered another previously unidentified small moon and an additional ring of Saturn. It crossed the orbit of Neptune on February 25, 1990, becoming the fourth spacecraft to do so. Voyagers 1 and 2, which traveled much faster than either Pioneer mission, quickly caught and surpassed 11 before reaching Neptune's orbit. Routine contact was made with the spacecraft until September 30th, 1995, by which time the spacecraft had been shut down. NASA would keep communications with the spacecraft going until November 24th of that year, when the last signal was received. Pioneers 10 and 11 and the other spacecraft of the Pioneer program paved the way for our understanding of the interstellar medium and outer solar system, collecting invaluable data on planetary atmospheres, radiation environments, space weather, and cosmic rays. These missions laid the foundation for the future of planetary exploration. Perhaps the most memorable part of the program was the legacy of the Pioneer plaque, a small memento of humanity meant for extraterrestrial life. First thought up by journalist Eric Burgess, the idea of the plaque was then conveyed to Carl Sagan, who became enthusiastic at the thought of sending a message into interstellar space. Sagan was not the first to note that 10 and 11 would leave the solar system, but he was the strongest advocate for including a message given this fact. NASA agreed to include a message and gave Sagan 3 weeks to prepare it. Him, his wife, and scientist Frank Drake designed and prepared the plaque, with contributions by artist John Lomberg. 2 plaques were made, each launching on Pioneers 10 and 11. The plaques measure just 6 inches high and 9 inches wide. Made of gold anodized aluminum, they're designed to withstand the intense conditions of space and provide a long-lasting message intended for extraterrestrial life. On the plaque are several symbols. At the top left is a schematic of a hydrogen atom's electron spin, which occurs every 0.704 nanoseconds. Extraterrestrial life can utilize this fact if they understand the symbolism and know the necessary information to make sense of other depictions on the plaque. Using a single spin's time as the binary unit 1, it can also be inferred to be a unit of length of 21.106 centimeters, or the distance that light travels in 0.704 nanoseconds. Looking at the other symbols, these binary units can be seen all over the plaque. Next to the figures of a man and woman, the binary for 8, or 1000, can be seen. This means that the human is 8 times 21 centimeters tall, 1.68 meters, or 5 feet 6 inches. The humans in the plaque can also be seen standing in front of a diagram of the Pioneer spacecraft to reference size. Finally, a raised right hand by the main figure is intended as a sign of goodwill and also shows the mobility and design of the human body. Covering much of the plaque's left side is a complex depiction of the sun's location relative to local galactic landmarks. 15 lines emerge from the same origin, 14 of which have long binary numbers corresponding to each, and the 15th extends to the far right behind the human's figures. The line's lengths indicate relative distances from the sun toward nearby pulsars, whose pulse period are defined by the binary inscriptions, and the 15th line, unmarked, indicates the direction to the center of the Milky Way. Lastly, at the bottom of the plaque is a diagram of the solar system. Each of the planets, including Pluto, which was designated a planet at the time, is shown. Saturn's rings are also depicted to differentiate from the others. Binary numbers appear alongside each planet, showing their relative distance to the sun, and a miniature depiction of the spacecraft leaving the solar system is shown, with an arrow pointing from Earth to it, showing the path taken. The plaques were not changed for each spacecraft, so the depiction is inaccurate for Pioneer 11, which took a different direction out of the solar system than shown. But the plaques would go on to inspire the famous Voyager Golden Records, which include a similar depiction of the galactic map and the hydrogen atom diagram on their covers. As they race away from the sun, both Pioneers 10 and 11 are just 2 of 5 spacecraft on a trajectory out of the solar system. Though they're out of contact today, Pioneers 10 and 11 will continue the last phase of their mission for eons, sailing deep into interstellar space. If undisturbed, they will pass by distant targets, 10, which will reach the star Aldebaran in 2 million years, and 11, which reached the star Lambda Aquilae in 4 million years. The Pioneer program spacecraft may have been modest compared to modern ones, but their significance cannot be overstated. Pioneer broke new ground, both literally and metaphorically, in the exploration of interstellar space and the outer solar system. These missions demonstrated the possibilities of robotic exploration and laid the groundwork for more complex and ambitious missions. Today, every interplanetary probe traces its origins back to these early pioneers. Thank you for watching. If you enjoyed the video, please leave a like and be sure to subscribe for more releases.